Let me ask you something. You know that incredible machine sitting inside your skull? Your brain. Well, it runs your entire life, your thoughts, your memories, everything, on less power than a dim light bulb. So how's that possible? Today, we're diving into a computing revolution that's trying to copy that exact trick.
Okay, so let's jump right in. The whole thing starts with what I call the 20-watt problem. And trust me, it's a problem that's pushing our current AI to the absolute breaking point.
20 watts. That's it. That's the number. It sounds ridiculously small, right? But that's all the power your brain needs to do, well, everything. To think, to dream, to remember, to be you.
Now hold that number in your head, 20 watts, because when you compare it to our best AI supercomputers, it's just insane. We're talking about machines that need a small power plant just to operate, and they can't even do a fraction of what your brain does. That massive gap, that's what's forcing a total rethink of how we build computers.
So what do you do when you're faced with a problem like that? Well, you cheat. Engineers are basically looking at biology's 3 billion year head start and saying, yeah, we'll have some of that. They're literally trying to copy nature's blueprint and etch it right into silicon.
And this whole idea has a really cool name, neuromorphic computing. And let's be clear, this isn't just about writing smarter code. No, this is way deeper. It's about tearing up the old designs for computer chips and building completely new ones from the ground up. Chips that are designed to work just like the neurons in your brain.
Someone called it biology's cheat code, now in silicon. And I just love that. It's perfect, right? We're not just getting inspired by nature. We're literally stealing its best trick to build the next generation of computers.
Okay, so thinking like a brain sounds cool, but what does that actually mean? How in the world do you get a piece of silicon to act like a neuron? What's the secret sauce here?
All right, it breaks down into a few key things. First, your computer right now, it's always on, always calculating, burning energy. These new chips, the neurons only fire when something actually happens, when there's new information to process. Super efficient. Second, they get rid of the biggest bottleneck in computing. They put memory and the processor right next to each other, in the same place. This means they can learn right on the device, no need to phone home to the cloud. And the result of all this? They sip power. We're talking microwatts, not kilowatts. It's a whole different universe of energy use.
Okay, that's the theory. But you're probably thinking, how much better is it really? Like, what happens when you put one of these things to the test on a real-world job? Check this out. This is a simple test, just spotting a key word. You know, like when you say, hey Siri. A normal chip uses somewhere between 10 and 50 milliwatts. The neuromorphic chip? It uses between 100 and 500 times microwatts. Just so we're clear, a microwatt is 1,000 times smaller than a milliwatt. The difference isn't just big, it's absolutely staggering.
Let me put that in a way that's even crazier. With that level of efficiency, you could have an AI that's always on, always listening, running for months on a single tiny hearing aid battery. Just think about that. It completely changes the game for what you can build into small devices.
And this isn't just about tiny gadgets. The same logic scales up. Imagine data centers that don't need their own dedicated power plant to run. We're talking about creating whole new categories of devices that were just a fantasy yesterday because they would have needed a car battery strapped to them.
And look, this isn't just some pipe dream stuck in a university lab. There is a full-on race happening right now to build this stuff. Let's see who's in the running.
You've got the big guys, of course. Intel is in the game with a chip called Low-IE2. BrainChip is another big name. But you've also got this whole ecosystem of super smart startups like Inotera and Synsense jumping in. The point is, this is real. The silicon is being made, the systems are being built as we speak.
So where does this all lead? What's the big picture here? When you step back and look at this massive shift, what's the real takeaway?
There's a quote I love that sums it all up. History doesn't crown the greediest machines. It crowns the ones that barely need to eat. For so long, we've just solved problems with brute force, more power, bigger chips. But that whole approach is hitting a wall.
Think about it. The age of just add more power is pretty much over. It's just not sustainable anymore, financially or environmentally. We can't just keep building bigger and bigger data centers that consume the energy of a small country. Something has to give. And that's why the next great computing empire, the next leader in AI, isn't going to be the one with the biggest, most power-hungry machine. No, it's going to be whoever can figure out how to think like a brain on pennies of electricity. And here's the kicker. This isn't some far-off sci-fi future.
This revolution isn't coming, it's already here. It's been running inside your head your entire life on just 20 watts, and now it's finally starting to run on silicon.